Arson refers to the act of unlawfully setting fire to property, structures, and other objects. It is considered as a serious criminal offence in most jurisdictions due to the potential harm it causes to people, animals, and the environment, as well as the destruction of property. Arsonists put out the fire by putting ignitable liquids such as gasoline, kerosene, lighter fluid, paint thinners, and other less common fuels. In criminal cases, the debris from fire were used to determine its ignitable liquid. Instruments such as NMR spectroscopy, fluorescence spectroscopy, UV visible spectroscopy, and gas or liquid chromatography are usually applied. In this report, ATR-FTIR was used to detect the ignitable liquids, which are kerosene and gasoline, that was used to ignite fire to A4 paper samples.
The application method: few pieces of blank A4 paper, kerosene, and petrol oil were prepared. The A4 paper was dipped into kerosene in a small amount and then repeated with petrol oil. Both of the papers were burned by using a lighter. Next, the ashes of the burnt paper were collected as much as possible into a petri dish that was placed 5 cm below the paper. As a preventive measure, the experiment was done in an open space to prevent fire and triggering smoke alarm. The kerosene ashes, petrol ashes, kerosene oil, and petrol oil were analyzed by FTR analysts along with an unburned A4 paper to be used as a control.
In this study, FTIR spectra were used to compare the chemical compositions of A. Kerosene ashes, B. Raw kerosene, and C. Paper as a control. For kerosene, the absorption peaks shows the CH ratings, which the main component of kerosene is. Kerosene consists of C6H14, which implies the aliphatic hydrocarbon, which contain chemical leakage of carbon to carbon and carbon to hydrogen. For the raw paper, which is act as a control, the main component is 90% to 99% made up of cellulose. This shows the absorption band between 1100 to 900 cm-1 is attributed to the CC double bond searchings and CCO searchings and COC searchings due to the presence of cellulose. However, compared to the paper ashes spectra, some absorption peaks that indicate the chemical component of raw kerosene and raw paper are absent. There are less absorption peaks at 1200 cm-1 to 800 cm-1 regions, resulting to the cellular degradations where the COC ratings was absent due to the heat decompositions. Furthermore, there are no absorption peaks indicate the presence of CC and CH bonding, while there are new strong absorption peaks present at 1394.87 cm-1, which corresponded to the OH bonding. There is also a new peaks at 871.52 cm-1 due to the C double bond C bendings of alkene groups. Due to the impacts of ignition source, lead to the evaporatings of paper components during the combustions. Therefore, the FTIR spectra results show the functional group present. However, the groups are insufficient to identify the actual types of accelerant employed due to the accelerant being destroyed at high temperature.
Petrol can be found at carbon 4 to carbon 10 in distillation crude oil. Petrol is ignitable liquid oil used in arson because inexpensive and readily available. Petrol composed of N-paraffin, naphthalene, aromatic, and isoparaffin. The compound present in FTIR analysis of petrol are alcohols, alkenes, alkynes, and amines.
However, the intervention of spectra proof gelatines and several materials displayed some variance across the various decomposition techniques. Thus, the FTIR method required destructive sample preparation techniques, and the approach was also more suited for the fibers rather than a paper.
In conclusion, the forensic chemical investigation into the use of petrol and kerosene as fire accelerants on A4 paper proved successful. The ATR-FTIR was utilized to analyze the arson residue and find out whether the functional groups of the experimental accelerants were present. The presence of the kerosene and petrol is shown by the result that demonstrate this method succeeded in identifying the functional groups of the compounds left in the fire residue. However, the results for this technique are insufficient to detect the specific kind of accelerants utilized. Therefore, in terms of its capacity to recognize functional groups in accelerants, this method fulfills the demands for fire debris analysis. The best instruments for identifying the original material and the accelerants involved in fire debris analysis, according to research studies, are gas chromatography mass spectrometry. That's all from us. Thank you.